Balance. The moments of a probability distribution have to do with its balancing points. Today, we will learn about a method for building estimators, which is called the method of moments. Basically, we compute the sample moments, like the sample mean, the mean of the squared sample values, and then we ask, under which parameters does the population distribution have the same first couple of moments? If we want to estimate, say, 3 population parameters, we set the first 3 sample moments equal to the first 3 population moments, getting 3 equations, and we solve that system of equations for the method of moments estimators. So now we're going to look at a couple ways of actually building estimators. Until now, we have not paid a whole lot of attention to building estimators. We've been given some estimators, and then we have looked at their properties like bias or variance or mean squared error, or whether they're consistent or not. But those estimators were kind of given to us, or we found them based on some intuition. But in this last set of lecture notes, we're going to discuss 2 methods of finding estimators. The first one is the method of moments, and the other one is called maximum likelihood. So we're going to spend a couple of days on method of moments estimators. What are these all about? Here, this is kind of like a moment arm, so this thing is sort of balancing. So that's why I put it there. The setup is like we have a random sample from some distribution, and the distribution has some parameters. So we're going to see lots of examples, but we could have some number of parameters like d, different ones, and we want to find functions of the data values x1 through xn to estimate the parameters. So the method of moments is based on what are called sample moments and population moments. So we've learned about moments before in terms of like the expected value of a random variable, the expected value of the square of a random variable, and so on. Those are going to be like the population moments, and those population moments have sample versions, and we'll see what those look like in a second. And so what we do with the method of moments is basically we ask, what are the values of the parameters under which some of the population moments are equal to the corresponding sample moments? And we set as many of them equal as we need to in order to find estimators for our unknown parameters. Okay, let's flesh that out a little bit. So officially, the method of moments estimators are the solutions to some equations. We have some familiar quantities here. So if our random sample is the values x1 through xn, then this thing here is like the sample mean. And we're going to call that thing the first sample moment. First sample moment. And so if I think of a random variable x having the distribution from which the random sample is drawn, the expected value of x is known as the first moment, but we're going to call it the first population moment now that we're talking about population and sample. So first population moment. Now if my random sample comes from some distribution, say depending on the parameters theta 1 through theta d, then the expected value of x, this one, is going to depend on the values of those parameters. So we're using this notation mu1 prime, and we're emphasizing that it depends on these parameters. We'll see examples of this. And so if we raise things to the power, to different powers. We could have like some of the xi squared values here. We would denote this as m2 prime. So this kind of colon equal sign means we're defining something. And so we would call this thing m2 prime, and that's equal to, we set it equal to the second population moment, which we would denote by mu2 prime, and that's also a function of the parameters. So these equalities here, we just set these equal, and then we solve for our unknown parameters theta. So we basically solve equations for theta 1 through theta d in terms of the sample moments m1 prime to md prime. Okay, so here the sample moments we denote with these m's, the population moments we denote with these mu's. And so the method of moments estimators are the parameter values under which the first d moments between the population and the sample are set equal. That slide might look a little bit confusing. Let's jump right into an example of this. Okay. So here we have a really familiar situation. We've got a random sample from the normal distribution with parameters mu and sigma squared, and we want to find the method of moments estimators of those parameters. Okay, so what we're going to do is my sample moments are m1 prime, which is the sum of the xi's. That's called the first sample moment. The second sample moment is equal to the mean of the squared values. Okay, so now I've got two population parameters to estimate. So what I'm going to do is set up two equations with two unknowns, and then I'm going to solve for those. So I'm going to set this equal to mu1 prime, and I'm going to set this equal to mu2 prime, where this mu1 prime is, remember, the first population moment, first pop moment. And that means it's like expected value of x, where x follows this normal distribution. And so the expected value of x we know is this parameter mu. Okay. Now, for the second one, we're going to set the second moment equal to the expected value of x squared. Okay, and now I want to write down expected value of x squared in terms of the parameters mu and sigma squared. So in order to do that, I'm going to remind myself that I can get the variance of a random variable by taking the second moment minus the square of the first moment. Because here I'm trying to get a second moment. So I can rearrange this so that I can see that the second moment is equal to the variance of x plus the square of the first moment. The variance is sigma squared. We know that about the normal distribution, and the mean is mu. So here I get mu squared. So here I have sigma squared plus mu squared. Okay, so I've got some equations here. Let's write it down in kind of a neater way. So basically what we have is just the first sample moment. I'm setting this equal to mu, and I'm setting the second sample moment equal to sigma squared plus mu squared. Now, these things can be computed from the data. So remember, these are the sample moments, which means I can compute them from the data. So now I have two equations and two unknowns, and I'm just going to solve for the unknowns. That is, I want to write mu equals something and sigma squared equals something, where over here I have only sample moments. So I get mu is just equal to the first sample moment. Sigma squared, if I rearrange this equation, I get this is the second sample moment minus mu squared, subtracting this mu from both sides. But then mu is going to be the first sample moment, so I'm going to put m1 squared. Okay, so the method of moments estimators for mu and sigma squared are given by that. We might want to write them down with more familiar notation. So for the method of moments estimators, I like to put a bar on top of them so that we kind of know. Let me put the bar kind of over the square. So our mu bar, our method of moments estimator for mu, is the first sample moment, which now let's write it like this, but that's x bar. So let me write it as x bar. That's kind of a more familiar way of writing the first sample moment. And sigma squared bar, our estimator of sigma squared, is the second sample moment minus the first sample moment squared, just taking it from here. So this m2, remember, is the mean of the xi's squared. Okay, let's make this look like something a little bit more familiar. By some rearrangement, we can show that this is equal to the sum of xi minus x bar squared, I going from 1 to n. Okay. That's with a few steps that I know we've done it at some point in this class. Okay, so these are my method of moments estimators for mu and sigma squared. What do we notice about them? We're kind of used to seeing for our estimator of the variance. We're used to seeing division by n minus 1 instead of division by n. Okay, so our method of moments procedure, which is kind of a recipe for getting an estimator, it gives us something different from the estimator that we're maybe used to using. But it's not that different. I mean, it's just division by n instead of by n minus 1. Okay, so we've found the method of moments estimator. Our second task is discuss whether better estimators might exist. Okay, so let's discuss that. For mu, so can there be better estimators? Well, for mu, I know that x bar is unbiased. We know that. In addition, we also know that the sum of the xi's, or I think we showed actually directly for the mean, that the mean is a sufficient statistic for mu. or to be very precise, we showed together that x bar and Sn squared are sufficient for the pair mu sigma squared. So here for mu I have an unbiased estimator, and it's a function of a sufficient, so based on a sufficient statistic. So this means it's a special kind of estimator, which is the minimum variance unbiased estimator. So that is nice. For sigma squared, my estimator, this guy, is actually not unbiased, okay? It's biased, so is biased. How do I know that it's biased? I know that it's biased because expected value of this Sn squared is equal to sigma squared. This Sn squared is my unbiased estimator. Okay. And if I look at this method of moments estimator, I can write it as n times n minus 1, or rather n minus 1 over n. N minus 1 over n times Sn squared. Why can I do that? Let's write it out. So I've got, this is my estimator, my method of moments estimator. If I multiply by n times n minus 1, or then, okay, hold on. If I write 1 over n minus 1 here, and then multiply by n minus 1, then this is Sn squared. So I see that it's n minus 1 over n times Sn squared. Okay, so expected value of my method of moments estimator is actually n minus 1 over n times expected value of Sn squared, which is n minus 1 over n times sigma squared. So I tend to underestimate the variance by a little bit using the method of moments estimator. So it's biased. It is based on a sufficient statistic, but it's a biased estimator. It doesn't necessarily mean it's terrible. We've seen some biased estimators which are very good, but if we're asking, is this kind of the best one, we might say, well, I mean, why don't we just use this sample variance, because we know that it's the MVUE. Okay, I think we showed before that this one is the MVUE. So the method of moments recipe for estimators does not always give us the MVUE, but it can give us reasonable estimators. Let's do another example. How about the gamma distribution parameters? Let's say we have a random sample from the gamma distribution with parameters a and b. So all we have is a bunch of numbers from our random sample, and we want to know how in the world could I estimate the values alpha and beta. Maybe I just call them a and b. They're alpha and beta. Okay, so find the method of moments estimators. Our first task. What we're going to do, since I've got two parameters, I want to set up two equations. So I'm going to set the first sample moment equal to the first population moment, and the second sample moment equal to the second population moment. And let's emphasize that these are functions of alpha and beta. This is like expected value of x. This one is like expected value of x squared. All right. So if we look at the gamma distribution cheat sheet, in our cheat sheet table, we find that the expected value is alpha beta. The variance of a random variable x having this gamma distribution is alpha beta squared, which means the second moment is equal to alpha beta squared plus the square of alpha beta. Because, remember, I can get the second moment by taking the variance and adding the square of the first moment. So here I'm going to write alpha beta squared plus the square of alpha beta. Now, I want to solve my system of equations so that I get alpha and beta in terms of the sample moments. And then I'm going to call them my method of moments estimator. Okay, so I'm setting these sample moments equal to these population moments, and solving to get the values of the parameters under which these equalities hold. Okay, so alpha, so from this top equation, it looks like I can take the first sample moment and divide by beta, whatever beta is going to turn out to be. And so we have to kind of play around here. Let me plug this into the second one now. So M2 equals, now I'm going to put M1 prime over beta, beta squared. I'm plugging this into alpha of the second equation. So plus M1 prime over beta, beta squared, which gives me M1 prime beta from the first term and M1 prime squared from the second term. So now I can finish solving this one for beta. So I get beta, so let me just carry this down. Okay, so this I can rearrange to get M2 prime minus the square of M1 prime over M1 prime. Okay, and I'm going to call that my beta bar. And now I can plug this into here to get my alpha bar. So alpha bar was M1 prime divided by beta. And so I'm going to put all of this in here. So all of that goes down into the denominator. So when I simplify that, I'm going to get M1 prime squared divided by M2 prime minus M1 prime squared. And that's my alpha estimator. Let's write them using quantities that are a little more familiar to us. All right, alpha bar first. So this M1, remember, is just x bar. So I'm going to get x bar squared divided by, and this thing we have seen before. We've dealt with the second sample moment minus the square of the first sample moment. Let's scroll up to wherever we saw it. Second sample moment minus the square of the first sample moment. That was this thing. It was like the sample variance, but divided by n. Okay, so I can put down here this. I can write it, I can just leave it like this if I want, but sometimes it's nicer to see it like this because it involves things that maybe look more familiar. Beta bar is, okay, in the numerator we have this same thing again. That is going to be this sample version of the variance. So the sample variance with divisor 1 over n instead of 1 over n minus 1. And here I've just got my x bar. So those are my method of moments estimators for alpha and beta. So these are my moms. Wow, those look complicated. Discuss in part 2 whether there might be some better estimators of alpha and beta. Well, so I don't even want to begin to compute the expected values of these estimators. That would be really, really hard because we're dealing with like a ratio of things of which we don't really know the distribution well. So let's not even think about doing that. What we might notice about them is that actually each of these sample moments, like this M1 and M2, so remember M1 prime, let me come down here. So M1 prime is this, M2 prime is this, and this alpha bar and beta bar, they are functions of these sample moments. It turns out that these sample moments are consistent estimators for their population moments. In this situation. So we have some theorem which says that if I have some estimators which are consistent for some parameters, then if I want to estimate a function of those parameters, I just need to take the same function of my estimators and it will also be consistent. So here I've got this function of sample moments and this function of sample moments. By the consistency of each of these sample moments, what I can say is that this is a consistent estimator of beta and this one is a consistent estimator of alpha. So that's good. We like our estimators to have consistency. Are they, though, the best possible estimators? Well, maybe we should ask, are they the MVUEs for alpha and beta? So at some point in the last lecture, we figured out, or maybe it was in a homework, what are sufficient statistics for alpha and beta? So we should ask, are they based on sufficient statistics? Let's see if they are. So in order to find sufficient statistics, I've got to write down the joint PDF of the random variables in the sample, which is going to be the product of these densities. I'm going through this part a little bit quickly because I think we've done this before. We have found sufficient statistics for the gamma distribution before. So letting that product do its thing, I would get all of this constant raised to the power n. Then I would have product of the xi's raised to the alpha minus 1. Then e raised to the negative sum of the xi's divided by beta. And then product of these indicators. And so by the factorization theorem, this is like my G, this is my H, I can say that this and this as a pair So the product of the xi's and the sum of the xi's is a sufficient statistic for the pair of parameters alpha and beta. Okay. Knowing that, I can ask myself, are these method of moments estimators, is it possible for them to be the minimum variance unbiased estimator? So first of all, I don't know if they're unbiased because it's too scary to compute their expected values. But do I have any hope of their being the minimum variance unbiased estimators, even if they were unbiased? Well, these estimators are based on the first and second moments, which are these quantities. This first one appears in our sufficient statistic as one of the components, but our work down here tells us that if I want to keep all the information in the random sample about alpha and beta, I need to look at the product of the xi's. And my method of moments estimators do not use anywhere the product of the xi's. That means that when I compute these method of moments estimators, at some point I'm throwing away some important information. I'm not using all the information in the data. So something that tells us that the method of moments estimators, even though they're consistent, they might be kind of good estimators, but they're probably not the best thing out there because they don't use all the information in the data. Okay, now we're gonna see what it looks like in practice to compute the method of moments estimators. Okay, so we're gonna read in a bunch of data. So I've got this data in this vector x. We could make a histogram of it. It looks like this one. Okay, so we might assume that this follows a gamma distribution because all the values are positive, and we can sort of imagine that it's right skewed. So let's go ahead and compute our method of moments estimators. So let's call the first one alpha bar and the second one beta bar. First, let's compute the sample moments. So to get the first one, it's like mean of the x's. The second one is just mean of the x squareds. Okay, so my alpha bar was like m1 squared, so I'm using the expression where I left it as the m's, m2 minus m1 squared. And my beta bar was like m2 minus m1 squared. All of that stuff divided by m1. Okay, so I get the values alpha bar and, sorry, that's other stuff down there, and beta bar. Okay, that might not be very informative, so let's draw a picture. So on top of my histogram, let's see, I think I want this to be false. I want to make some, I want to draw the PDF of this gamma distribution under these choices of the parameters. So I'm going to do lines, density of the gamma. I'm going to put in a sequence of x values. So let's make a sequence of x values beginning at 0 and going up to like 10. No, it has to go up to like 20 because my histogram goes up to 20 over here. Length, let's just do like 300. And so the shape is going to be alpha bar, and the scale parameter is going to be beta bar x sequence. Okay, I've got to make it find my x sequence first. Okay, so here we have it. I've got my histogram, and now under the method of moments estimators, I get this PDF which is overlaid. That is the PDF of the gamma distribution with alpha and beta given by these numbers. So to reiterate what the method of moments estimators are, if I look at this sample of data, it has a mean of 7.72, and the mean of x squared is 72. If I look at this, this PDF, that PDF has expected value of exactly 7.72, and the expected value of x squared of this gamma, according to this gamma PDF, is exactly 72.24. So we have asked which gamma PDF gives me exactly the same moments as the sample. Okay. And so that's what it looks like. Let's do one more example of the uniform distribution on 0 up to theta. So probably getting tired of this example now, but whatever. So we've got a PDF which looks like this, and we've got x1 through xn coming from here. And we want to find the method of moments estimator of the parameter theta. Okay, so what we're going to do, we only have one parameter to estimate. So we only need one equation. So I'm going to take the first sample moment, set it equal to the first population moment, which is going to be some function of this parameter theta. And it's going to be theta over 2. That's the first population moment, because expected value of x, if x has the uniform 0 theta distribution, that means the expected value of x is theta over 2, because this is like the balancing point of the density. Okay, so my first sample moment is just x bar. So solving that for theta gives theta bar equals 2 times x bar. And this is the method of moments estimator for theta. Okay, so that was number 1. We found it. That was not bad. Number 2, discuss whether a better estimator might exist. We've had a lot of discussions about this particular situation. I think we've looked at the estimator, which is taking the largest order statistic, and we have compared that estimator to this one already in the past. In the past, we didn't know that this estimator had a name as the method of moments estimator, though we have studied it before. And if you remember, we found that that this estimator has a smaller mean squared error. Okay. Another way we could kind of gain insight into whether this method of moments estimator is a good one or not is to ask the question, is it based on a sufficient statistic? Okay, let's try to figure out if it's based on a sufficient statistic. I don't know if we've done that yet. To figure out if it's based on a sufficient statistic, we need to write down, so we're going to find a sufficient statistic for theta. To do that, we have to write down the joint PDF of the random variables in the sample. So that's going to be the product of 1 over theta, so the density is given by 1 over theta. And then let's put these indicator functions here to remind us that the support is on xi, the support is on 0 to theta. So we're going to get 1 over theta to the power n times this product of indicator functions. And here it starts to be a little less obvious, or not so obvious, how we find the sufficient statistic now for theta, because this looks a little bit strange. Well, what we find is that if I write this, it's like the product. Well, so let me just write this whole thing. So we've got 1 over theta to the power n, and then I've got the indicator function telling me whether x1 is between 0 and theta, the indicator function telling me whether x2 is between 0 and theta, and so on, all the way out to the indicator function telling me whether xn is between 0 and theta. Now, this thing is going to be 0 or 1. This will be equal to 0 or 1. This will be equal to 0 or 1. So this whole thing will be equal to 0 if any xi is not in the interval 0 to theta, and will be equal to 1 if all the xi values are in the interval from 0 to theta. 0 to theta. Okay, because it just takes one of them to be 0 for this whole thing to be 0. So I can say something like an indicator function which is all the xi's are in the interval 0 to theta. Or, if I think about it, drawing my picture of the density again, 1 over theta. If I think about order statistics, I'm going to have the first one, the second one, and so on, and over here is the nth one. I know that the first one is the smallest, and then all these other ones are in the middle, and then xn is the biggest. So if all of them are between 0 and theta, I can write this as the smallest one has to be greater than 0, and I know the largest one has to be greater than the smallest one, and that one has to be less than theta. Okay, so I'm able to write down the joint PDF like this, and that tells me that the pair of order statistics x1 and xn is sufficient for theta. Actually, I don't even need this first one. Because, let me simplify it even further. I don't actually need both of them, because I can write this as 1 over theta to the power n. I can put an indicator that xn is less than theta, and then I have over here that x1 is greater than 0. And so by the factorization theorem, this is like my function g of xn and theta, and over here this is my function h of just the data but not involving the parameter. So by the factorization theorem, actually, I can say that the largest order statistic is sufficient for theta. Okay, so by factorization. This kind of makes some sense, I think, because it's like, if I know xn, knowing these other values does not give me any additional information about the parameter theta. So now we can go back and answer this question in a more informed way. Is 2 times x bar going to be a really great estimator of theta? Is it going to be the best? Well, it does not use the value of the largest order statistic. I mean, it averages all the values, but it's kind of like the wrong summary of the data. If we really want all the information in the sample about theta, we need to be looking at the largest order statistic, not at the sample mean. Okay, so because of that, since the method of moments estimator is not a function of a sufficient statistic, it's not going to be the best. It does not use the most informative feature of the data to estimate its parameter. So, so somehow this estimator is better. The method of moments recipe does not lead us to this better estimate. And remember, we were able to find an unbiased version of this other estimator. So I think we looked at this before. If I take n plus 1 over n times the largest order statistic, and I call that thing theta tilde, then theta tilde is unbiased, and it's also the minimum variance unbiased estimator because it's a function of a sufficient statistic, Okay, so again, the method of moments kind of gives us an estimator which makes sense, but it doesn't use the data to full advantage. Yeah? Okay, you can go through.